Okay, so we're over halfway into this class and we're finally getting into what's going on during exercise. So we're going to talk about cardiovascular adjustments, and there's only two videos for Tuesday, but there will be 4 for Thursday, but the amount of material is about the same. So here are the 3 outcomes that we've got for this lecture. So when it comes to exercise, there are 3 things that have to occur if you're going to do large muscle mass exercise. And so those 3 things are the autonomic nervous system has to change so it can increase cardiac output. That cardiac output has to be redistributed, and we have to make sure that we increase venous return to match that increase in cardiac output. Because if we increase cardiac output but we don't bring the blood back, that's not going to be very beneficial. So if we look at this figure here, and this is right out of your textbook, notice that as we increase VO2 or intensity, and it's shown here in terms of percentage of VO2 max, cardiac output increases pretty linearly. And as we discussed the first day of the cardiovascular unit, typical cardiac output's about 5 liters at rest, and depending on who you are and your size and that sort of thing, and your training, that can increase anywhere from 4 to 8 times. So that 5 liters can become 20 to even 40 liters a minute, which is quite a bit. The problem is, and we're going to get into this more at the next video, is that your VO2 goes from about 4 at rest to anywhere 40, 50, 60, 80, even 90 if you're an elite athlete. And so cardiac output's not the only thing, and we're going to get into that later. And so this leads us to Fick's law, and Fick's law just says that VO2 equals cardiac output times what we call the AVO2 difference. And so we know VO2 is just how much oxygen we're using, and Q is cardiac output, and then the AVO2 difference is the difference in the amount of oxygen in your arterial blood versus your mixed venous blood. Okay, so let's just say you go running and your heart rate's 180, your stroke volume's 200, and your AVO2 difference is 15. Well, what would your VO2 be? And so if you do the math here, this would give you 5.4 liters of oxygen per minute. And unless you're a pretty big person, this would suggest that you're probably an elite athlete. Okay, so that's a lot of oxygen to use, but it's possible. All right, so when it comes to this, we need to take into account oxygen content. And so the equation for that is 1.34 milliliters of oxygen per gram of hemoglobin times the concentration of hemoglobin times the saturation of hemoglobin plus 0.03 times the partial pressure of oxygen in your arteries. Okay, and so if we just use typical values of 15 and multiply that by 100% saturation, we'd be at about 20.4 mils of oxygen per deciliter of blood. And I'm missing that deciliter of blood here on my units. All right, now notice that we're a little bit lower than that because we're never actually 100% saturated. But I want you to take a look here and look at the difference, or what happens to several variables here. So we've got arterial capacity, which is the red line, arterial content, which is the blue line, and then we've got the mixed venous content is this purple line, and the difference between the blue line and the purple line is our AVO2 difference. A couple things. Capacity is just how much oxygen could we hold if we were 100% saturated. Content is what we're actually holding. So notice this one increases slightly, content stays relatively constant, AVO2 difference increases because mixed venous content decreases. All right, and so our capacity actually increases a little bit due to hemoconcentration as fluid leaves the plasma and enters the cells or enters that interstitial space. And so as a result, we have a greater concentration of hemoglobin. Content stays the same because saturation stays constant. There is a slight increase just because there is a slight increase in the hemoglobin concentration, but it's not a significant amount. And the same is true of capacity. This isn't something major. Mixed venous content decreases because we're using more oxygen. Okay, on the x-axis here, we've got VO2, and so when we're essentially at rest, we're 1 or even less than 1, whereas max exercise will be getting up to 4, 4.5, 5, depending on size and fitness. And so the AVO2 difference increases because, well, you're using a lot of oxygen as you exercise. So again, going from rest to exercise, heart rate increases with intensity until you reach heart rate max. Typical, maybe not the best, but a typical equation for that is 220 minus your age. Stroke volume increases with work intensity. In a typical individual, stroke volume actually taps out or maxes out around 40% of VO2 max, except in elite athletes. And really, it depends on the training state. So cardiac output will ultimately increase linearly. We've seen that before with work intensity. So it's like, remember, cardiac output is just a product of heart rate and stroke volume. That AVO2 difference, as we showed with the previous figure, is dependent on the intensity of the work as well. So keeping these things in mind, we're going to kind of take what we've applied here and then apply them to the next video. But can you do these two things? Can you explain the primary adjustments that have to occur during exercise? And can you summarize the Fick equation?